Can you hear me? Okay, well, everyone, thank you to all that are here in person. I'm Andrea Tapia. I'm the interim dean in the College of IST, and I am standing in for our associate dean, Carlene Maitland, who is not feeling well today, but is the organizer of these research talks. And so I have the great pleasure of introducing Hong Hu, who is an assistant professor in the College of IST. He's been here for 4 years, almost 4 years, and we haven't seen a presentation by him because he arrived during COVID, and I'm so happy that he is here and so happy he's presenting to us. Do we have people on Zoom too? Yes. No Zoom. Okay. So I'm going to introduce him now. Dr. Hong Hu is an assistant professor in the College of Information Sciences and Technology at Penn State. His main research area is system and software security, focusing on exploring new attack vectors of memory errors and developing effective defense mechanisms. His work has appeared in top venues of system security, including IEEE S&P, Usenix Security, CCS, and NDSS. He received the Best Paper Award from CCS in 2019 and ICE CSS in 2014. Dr. Hu obtained his PhD degree from the National University of Singapore in 2016. After that, he was a postdoctoral fellow and research scientist at Georgia Tech from 2017 to 2020. Please help me welcome him, and thank you very much.
Thank you, Andrea. Thank you. Finally, I'm standing here in history forever. So I know the pizza is outside, holidays next week. So I'm trying to make it the talk shorter, simple, and hopefully you can enjoy that instead of suffering from that. So today I want to introduce our very recent work, the spotting Syscall-Guard Variables for data attacks. Only this work, so it's going to be very quick. So I'm going to follow this schedule listed in the title. So first, we're going to introduce what is Syscall-Guard Variables. Yeah, that's a hard topic to explain. Let me try this again. Okay, so second is data attacks, and the last one will be how to spotify Syscall-Guard Variables for data attacks. So first of all, what is Syscall-Guard Variables? So we define it. So this is a new term. So Syscall-Guard Variables means the variables that got syscalls, right? So straightforward, easy to understand. Before you kick me, this is the common pattern to use Syscall-Guard Variables. So if a condition is satisfied, you can invoke a syscall. Otherwise, you cannot invoke a syscall. So we all know syscall, we call it system call, is the API, is the interface for user-space applications to invoke some service provided by the kernel. So this isolation is available for both Linux, Mac, or Windows, or any phone devices. So user-space application need to invoke system calls for some high privileged operation. For example, if you want to run a new application, you need a system call. If you want to read or write files, or you want to connect to network, you need a system call. If you want to operate some external devices like keyboard, camera, or even touch screen, you need a system call. So you may feel, well, this is just a normal operation, right? Why this is high privileged? Because this is very interesting from the security perspective. So if attackers, they have the ability to have this process, they can do a lot of interesting stuff. For example, if they can run any program, they want to run malware, right? To control your computer, to attack other computer. So FBI will find you, not them. And also, if they can read the files, they may want to steal your pictures, videos, steal your papers, your proposal, anything, right? They will even encrypt your files and ask you for Bitcoin. Otherwise, they'll never share the decryption key with you. And also, if they have the ability to operate on devices, they may want to turn on camera, turn on microphone, and they want to record all the things you have on the computer, including your password, username, bank account, social security number, and anything. So that's why we care about the system calls. We care about the permission. And then the Syscall-Guard Variables is a guard of syscalls, and actually they are guard of resources. So we can try to refine our definition. So Syscall-Guard Variables is actually the variables that guard the resources. Okay, so if the variable matches some condition, you can access the resource. Otherwise, you cannot. So this is a very strong protection against the resource. We can try to explain it using a very simple example. For example, if you want to log into FTP, do we still know FTP today? Anyone still use FTP? Cool. It's a protocol used a long time ago, not that long, but today we have so many cloud service. So FTP is to store files remotely and access it. But the login process is very standard. So today, even you log into the, say, Penn State website, you still need to use the browser to log into Penn State server. So through the request, and the server will give you a response. So this is very standard login process. So as you can imagine, the server are going to have some mechanism to verify you are you, right? And not someone else. So they have some functionality. Let's say this is a function called authenticated, called auth. So this code is on the server side, not on the client side. So this is a very simple way to implement the authentication. Super simplified, super insecure. So don't implement this way. It's for demonstration purpose. So the server will read from network. You want to read the username, read the password. It's all provided by the client side, by you, right? They're going to verify, okay, your username and password match each other and match our record, so you can log in. In that case, they're going to say, okay, success. You can log in now. Otherwise, they'll say, oh, no. So this is failed login. You should try again, or I'm going to block you. So this is a very simple functionality of authentication on the server side. So server, we're trying to have this big loop. This is the while loop, which means as long as authenticated flag is failed, you should keep invoking this function, keep authenticating, right? So in this case, if you don't know the password and username, you are being blocked here. You have to try again and again. Maybe after 3 times, you're blocked for a while. So this is a mechanism. But if you know the password and username, you can log in. So this is going to retain success, and this is going to bypass its fail, and going to break the loop, and you can get access. So in this case, if the user wants to run some command, the code will check, hey, is this user authenticated or not? If yes, yeah, go ahead and run the code. And if you want to view some image, they're going to check whether the user is authenticated or not. If yes, go ahead. And if the user wants to modify the profile, they're going to check whether they are authenticated or not. If yes, go ahead. So in this case, you can say this variable here, authenticated, this one remembers whether the authentication has been successful or not. And after the authentication, only this variable determines whether you can access these resources or not, right? So in this case, you can say this one is a guard. Before you can do any running command of your images or update profiles, you must make sure this condition is matched. You must make sure this variable is true, is a success. So in this case, we will call it a Syscall-Guard variable. And internally, inside this function, I'm going to call syscalls. We just skip it here. But we still call them Syscall-Guard variables. So you can say this variable is important. If you can modify this one, if you can flip this one, you don't have to log in. You can do whatever you want, right? Get access to resources. So this is our first milestone. We define the Syscall-Guard variables. These variables got the resources, got the permissions. And very common code pattern is like this. If the variable satisfies the condition, you can access resources. Otherwise, you cannot. Is there any question for this simple definition? Okay, so we can proceed to the second topic, attack. So the tag is called read-only attack because of some reason. We don't have to introduce that background, but you know this is a tag. So the tag is when attackers, they want to modify some Syscall-Guard variables. So we have mentioned this is a common pattern for the code to use these variables. They're going to check, hey, do you satisfy this condition or not? If you satisfy, you can access resources. Otherwise, you cannot. But for attackers, most of the time, they don't have the credentials, don't have information, right? That's why the attackers, they want to bypass all the defense and get access. But by default, they don't have access. So in this case, if they try to access the privilege, if they try to access the resource, they may go through the else, right? The otherwise pass, say, hey, you don't have access, you don't have the permission to access resources. So this is the common case. However, if attackers are able to modify the variable this way, so you take a negation of the variable and assign to this variable again, which means you just flip it. And now if they want to try again, you say they're going to match the condition, right? The condition is satisfied, and they're going to access the resources. So this is the attack. They want to modify variable, and they can get access. So this is the secret of data attacks. So the goal is that they want to break the guard, they want to get access to resources, they want to do something crazy, malicious, hacking, all of this. So we know this is a data-only attack. They just want to modify Syscall-Guard variables for some extra privileges. So let's use this example again to demonstrate what it will look like. So here, this example we use for login, and now we have a malicious attacker. They want to log into our account. They want to steal our information. They want to encrypt the files, asking for Bitcoin, but they don't know password, right? So if they want to hack into the server, there are two ways. They can keep trying. They can guess the username and password. Maybe the username is Honghu or Huhong or Hong or Hu. The password will be 1234, so on and so forth. They can keep guessing. But come on, I'm a security researcher, right? I don't decide the 123 as the password. So that's difficult for them to guess correctly. But they may find a different way. They may say, hey, I don't want to guess password, but if I can modify this variable, if I can modify this variable here, the same variable, you don't have to log in, right? It's already authenticated. If you modify this one to success, you can bypass this check. This loop is broken, and then you can bypass this check. You can run command, you can view image, you can update profiles. Whatever you want to do, you can do, because the application, the server believes you are authenticated, because the value of authenticated variable is the only thing they want to check. So this is attack. They want to modify this one and then to get access. So this is our second milestone. We understand that data-only attacks is where attackers want to modify Syscall-Guard variables and to get extra resources. Okay, is that a question? Okay, let's continue. So we mentioned attackers want to modify Syscall-Guard variables, but how do they modify? Is this even possible? The answer is very straightforward. Yes, it is, right? So that is the next part. It's about the memory safety issues. So this is the actual part of the second two. So memory safety issues is because all stems from this architecture. Okay, you need to go back to the very beginning. If you take the class for the first class of your computer science or IST, this is the architecture of a computer. Okay, so this is called the central processing unit, often called the CPU. CPU is in charge of calculations, do addition, subtraction, division, multiplication, logic operations. That's CPU. CPU is faster, crazy, and hot, but they cannot do storage. Okay, they have very poor capability for storage. They cannot store anything. They have to use memory to store data. Okay, so every time CPU want to calculate something, even 1 + 1, they must load 1 to CPU, another 1 to CPU, and they calculate, get 2, and they store the 2 into this memory. That's what the CPU is doing. So in this case, the memory is a location to store all the variables, to store the context, to store the status of the program. So that is the source of the problem, because memory is limited, right? So we know our computer, we have a 10 GB memory, 20 GB memory, but it's limited. But today we have so many huge, crazy applications to use all the memories. For example, Chrome, they use all the memories you have on the computer, like browser, like any Slack or Zoom or PowerPoint or anything you use. They want to use as much memory as possible. So there's a lot of competitions to use memory. So we have designed the memory managers to manage all the memories. So in this case, we want to make sure as long as the application want to use memory, we're going to give it memory, okay? The application don't have to worry about how to get the memory, because they just need to ask. If they ask, we're going to give them the memory. So we have the memory manager. The memory manager are going to allocate the memory from any free slots. As long as it's free, they're going to give it to you, okay? They don't care who you are. They don't care where you want to get the memory. As long as you ask, I'm going to give you any free memory. So in this case, for one variable, maybe the memory is allocated next to variable B. Maybe it's far from each other. That all depends on the memory manager. The program don't care about this. Program don't know this. So let's use the same example again. So we have, say here, we have the username and the password and authenticated. These are the variables, right? These variables must be in memory because CPU have no way to store them. So let's say this is a flight and a huge memory here. And we want to allocate some memory for username. And we want to allocate some memory for password. We also want to allocate some memory for authenticated. And this is looks like, okay? So this is one possibility, but it could be others. So this is memory. All the variables are stored in memory. And if we say we have the username password like this, it's who and 123. Let's say this one don't know security at all. You just set 123 as a password. So if you have this setting, if you provide this username and password, the memory are going to change to this way, right? This is the username, password, and this is the flag authenticated. It is successful because the username is and password is correct. And if we try a different one, admin 123, we know admin, they know security, right? Admin don't have 123 as password, so this is wrong password. But if you provide this, if you try this, you're gonna get this result: username admin, password 123, and the result is failed, which means login failed. Try again. So this is a normal operation. So successful login is allowed, failed login is blocked. It's perfect. However, if you're the attacker, you may want to try something crazy, right? Suppose say, hey, my name is admin, my password is this one. 1111111111111 success. Okay, what's going to happen? The computer, the machine, they don't know anything. Just hey, if you want me to store this memory, I'm going to store this memory. So this is the result. Oh, slice is wrong. No, because this is overflow. Because you only request this memory for storage, but you provide so many data, they cannot afford it, right? They have to keep writing, keep writing, keep writing. They're going to cross the boundary and keep writing. This is so-called the buffer overflow vulnerability. In this case, you can say you just need to provide a password, very long password, any password, long enough, then they are going to overflow and overwrite anything after it. So if you're the attacker, you can provide any password to override any data to any content, right? So you want to override this one to success, right? You say, hey, success. The program will check this variable and say, oh, success. Cool. Even if you don't have a chance to provide a correct password and username, but you still log in successfully. Okay. So this is the buffer overflow vulnerability. This is the attack. They're trying to override the memory and then get access. So this is one possible way. You may have heard about the term buffer flow, right? Maybe you take some security class, you heard about this name. And this problem is happening last century, about 40 years ago, 50 years ago. And when I talk to people, people say, what? This problem is not solved yet. We have so many solutions, so many attack and defense, so many money invested in this problem, but not solved. It's not solved. That's true. So based on recent studies, 70% of the Microsoft bugs from 2006 to 2018, and also 17% of vulnerabilities in Chrome, and 32 over 34 bugs, severe bugs in Mozilla, and also 67% of zero-day vulnerabilities in 2021, this year, are still memory safety issues, okay? So if you use Chrome, you still have this problem. If you use Mozilla, Mozilla, I think it's Firefox, right? You still have this problem. If you use Microsoft service, you still have this problem. It's not solved. They are full of buffer flow, use something free, have confusion, so on and so forth, okay? So which means attackers still have a lot of chance to find bugs and hack into your computer. So the way we are doing now is we're trying to find these bugs and fix it, okay? We're going to win the competition with the hackers. They want to find bugs. We also want to find bugs. If we can find them earlier, we can fix it, right? There's no way for them to exploit the bug as long as we are fast enough. So how to find bugs? We did some work. After we joined Penn State, we just did a bunch of works that try to find bugs in different systems. We don't want to talk about there's too many. So you can see we find bugs in database, we find bugs in Windows applications, in processors, in compilers, and in IoT device, in the Go program, in the PDF reader. Okay, this is important. We find bugs in Adobe Acrobat, Microsoft Word, and another PDF reader. We find 134 bugs, and we get money. So this vendor, Adobe and Microsoft, provide this $22,000 US as a bounty for us. And also keep doing this, we find one more bugs. So currently this is a very strong competition between attackers and defenders. We want to find bugs as fast as possible so we can fix it before they exploit it. But we don't talk about this. It's not the focus of today. So we want to go back. So basically, there's a lot of ways to find memory bugs. Attackers can find memory bugs. They can use memory bugs to build attacks. So they can find bugs and to modify the Syscall-Guard variables and to build attacks. Okay. So this is all what happened to attackers. Okay. So this is the second milestone we have. We understand data attacks. So finally, we get a chance to come to our research, how to find variables, how to find the Syscall-Guard variables, and to build data attacks. So it's not easy, because if you check this code, you must need to understand the code, right? Oh, this is username, this is password, this is a checking, successful, fail, this is authenticated. Oh, authenticated. You say, oh, authenticated seems to be interesting, to be critical, seems to control access. You say, hey, this is critical, right? You find it. You can manually check this. Take some time, maybe 1 minute or two. You can find this data. You can find this variable. But what about this? What's this? This is a call graph of the V8. It's the one component of our browser. So each dot here, you can see here, is a function. Each line here is function call. And this is the function call graph of V8. Okay? It's beautiful, right? But it's a nightmare for researchers because, wow, where to find the Syscall-Guard variables? I don't even see the code here, right? It's so small. So it's not possible to find it manually, or it will take 1 million years, right? It's like to crack the RSA. So this is challenging, we know, because there's no good pattern to find. There's no say, hey, you have to have this tab. You don't find any of them from a specific location. You must find them based on the high-level semantics, right? Oh, they got this. Oh, that's why they're Syscall-Guard variables, right? This definition is just straightforward. But the challenge here is in the large code base, it's almost impossible to find them by manual effort, right? So manual effort, that's not scale, we know. And we have some solution, rely on some particular patterns. But overall, the problem is not every program will have this pattern, okay? This will work for some programs, but not all. This is a problem. So in our work, we're trying to find a general solution that can find the Syscall-Guard variables automatically, systematically, and even to demonstrate they can be exploited. So we have this solution we call the branch false. This is a query name and also the probability assessment, how to pronounce. This is our solution to find this, solve this problem and find Syscall-Guard variables. And we build a tool, we find the unknown attacks, we find unknown variables and build attacks. So this is the most exciting part about this attack. This attack is against the SQLite and V8. Anyone use SQLite? Oh, a few of you. That's okay. All of you use SQLite. Because SQLite is embedded into the operating system, into browsers, into any tools, in Android, iPhone, you must use SQLite. So V8 is a browser engine, JavaScript engine, used by many. So this will affect a lot of users and applications. So let's look into what is the idea of branch false and how do we find the Syscall-Guard variables. Oh, we release our code. If you're interested, you can scan this QR code and get access. Our repo name is Penn State PSU Security Universe. It's lucky because the short name is also PSU. Okay, so this is example again. So we just provide a concrete real world example. And that is more concrete than the previous one. So here we have can quickly go through. So this is a flag authenticated. Still, this is the Syscall-Guard variable we want to find. We have this loop, right? Keep checking this variable. And here is authentication to verify username and password. And actually here in the real world program, this is a hash value of the password. So if you succeed, they're going to set the authenticated to 1, and then they're going to break the loop. You can get the success. So this function is going to read from network. This one is complicated. This one has a lot of code and a lot of bug. So here means attackers may jump in here and modify anything they want. So this is what bug happened. So we can find this one using fuzzing or simple execution or whatever ideas for bug finding. But here, we just need to know this one contains a bug. This bug will allow attackers to modify our memory, including this variable, okay? So we already know this is a critical variable because we understand its code. We go through together and we check them. But the question is, how do we find them automatically? We don't want to check code, right? Too much. Don't want to really see code. Crazy. So how do we find them automatically? We find some interesting observations. First thing is many of these similar attacks, they're going to using this finally using syscalls to achieve the malicious goal, to run programs, to change permission, to give some permissions to others. So this is necessary for user space application to achieve some privileged operation. So syscall is important here. You must reach syscall. Another observation is before the syscall, we have some checks, right? For them here, only if you match this condition, they're going to break, right? Otherwise, you keep running inside the loop, right? You're going to start here. You have no way to call this syscall. So this is second observation. So this is a condition. This is syscall. So both of them are required to build this attack. So that's why we propose this idea called Syscall-Guard branch and Syscall-Guard variable. So Syscall-Guard variable is used in Syscall branch to guard security critical syscalls. And this is our design of Viper. I'm going to introduce that. So there's some challenges. So first of all, is how do we know the sole contribution of a variable? So you can think about each program, even it's simple or not, we have a lot of variables, right? Even you run a simple input, it's a lot of variables being utilized. How do you know the sole contribution of one variable without considering others? So this is challenging. There's some solution, but none of them will be practical. For example, some execution is one tool. They can provide a path from beginning to the end. But they cannot tell you which one is important. They say, hey, this is the path. You can use that, but they don't know which one variable is the most important thing along the path. And also we want to be efficient and scalable. We want to support browsers. We want to support any program in the world. We can do analysis quickly. Static analysis is another tool, but cannot scale to support all of them. So here comes our solution. Our idea is quite straightforward. You understand that. So our idea is we're going to run the program and we're going to flip every branch during the execution. And then we watch what happens. That's it. So we're going to flip every branch that is triggered during the execution. We're going to hook the system call to say which system call you trigger. And we're going to check whether the flip will trigger new system call or not. If yes, maybe this is interesting. You should check them all. So this is our idea, very high-level idea. So for example, here we have the application. This could be the control flow graph or whatever graph they have. And given one input I, they're going to run, trigger one pass and complete, right? And then they're going to trigger a bunch of system calls. Let's say this one is syscall, all the syscalls triggered by this input, by this program. And then we're going to run the same program again with the same input, with the same environment. All the things are the same, except we are going to intentionally flip a branch at runtime. We can do that. We have technology to do that. And then we're going to let it go. Just keep running. They're going to do some other operation, go to different paths. They're going to trigger different syscall site. It's S1. Okay. So as long as these two sites are different, any difference must be caused by this flip. Right? Because it's the only thing we change. Input the same, environment the same, CPU the same, memory the same, all the things are the same. This is the only thing we modify. We just flip this branch. And then we just watch what happened. So any difference, any new system call here must be triggered by this flip. And this flipper triggers this new system call. So this is how we build connections between branches and syscalls. We keep doing this, we flip all the branch one by one. You can imagine it could be thousands of branches and millions of branches. We can do that. Okay, so once we find it, we're going to say, hey, this is likely connected, right? This branch could be related to syscall, but we want to confirm that. We want to use some measurement to make sure it is possible to flip this branch. So what we do is we're going to perform the backward data flow analysis to understand how this branch is calculated, which variable will affect this branch. We're just using a very standard way to do analysis to figure out all the memory locations that can affect this branch. And we're going to measure how likely attackers can use common bugs to modify this variable. Okay, we use our metric, for example, where they are. If they're global variable, they're going to be alive for the whole lifetime of process. So we can change it for any time. That's easier. For static variable, the variable only exists when you call this function. If you retain, that variable is gone. So in this case, you have very short time to modify this variable. That's harder. So we define this metric. Global variables is easier to be attacked than heap variables. It's easier than stack variables. And also we define the number of memory writing instructions within the lifetime of variable. So memory writing means that this instruction is going to access memory. And we assume every memory writing instruction could be abused by attackers to modify memory. We don't know. We don't know where's the bug. We don't know where's the exploitation. We just assume every instruction, every memory writing instruction may be abused by attackers. So in this case, if you have more instructions in the middle, you are more likely to be attacked. This is our assumption. So based on these two assumptions, we just measure, just estimate, just assess how likely one variable could be modified by attackers. By general, it's not specific to one bug. By general, common, and the popular vulnerabilities. Okay, so this is the second part of the design. So we implement the system. There's some complete design. I'm going to skip that. So all the goal here is to make it faster. So remember, we need to run thousands of, or even millions of executions of the same input again and again and again and again. But we want to make it faster by this design. We borrow some ideas from fuzzing and make it faster. And finally, we're going to get a bunch of results. So we say, hey, this is the branch, seems interesting. And this is the Syscall-Guard. This is the variable you want to modify to flip this branch. And this is the estimation how likely this variable can be modified by general memory errors. Okay, so based on this design, we just do evaluation on real-world programs. 20 programs from different sources. Some are well-tested. Some are used in previously known attacks. Some are huge programs. Some are for fuzzing benchmark. And we collect the input. All solutions require user provide input. We're going to use this input to run the program and flip all the branches. We have a bunch of ways to collect the input, quite standard. So this is our result. So we find 36 variables from 40 programs, and 2 of them, this one, are known to us before our evaluation, but all others, 34 of them are new. So all these variables here, listed here, is related to some very important system calls. For example, execute, which means that if you can modify one variable, you can ask the program to execute some new program for you, which means you can just launch malware, you can run any program here, do whatever you want. So this is why this is important. And unprotect can change the memory information. You can change the memory to both writable and executable, which is very important and malicious way to build more attacks. And this one is to rename files and delete files. This one to change the permission of files. So all of these system calls are related to permissions and the resources. So if attackers can modify any of this, they may force the program to call this system calls and achieve attack. Okay, so we also measured how likely to build attacks. So you can see this line here. You can a lot of circles. So the darker part means how likely we can build attack. And this one means we confirm this can build attack. This one is very likely, this one is likely, and so on and so forth. So we build this measurement. We use some emulation, just emulate some bug and demonstrate and show that whether we can build attacks, and all of them have the possibility to be attacked. We also investigated previously historical bugs to say if we have this bug, we can build attacks, and we confirm 16 of them, at least 16 of them, we can build attacks, and we build attacks. We build 4 attacks. So this is our evaluation to understand how likely we can build attacks from the result we find. We also measure the time, so which means if you want to analyze one program, how much time you need. We don't want to make it super fast because many programs are huge. For example, this is a V8. We need maybe 2 hours to finish, right? And this one is OpenSSH, also takes less time. But the question is, you just need a machine to do this analysis for you. And then you're done, right? You just need to take your coffee and waiting. Then they're going to tell you, hey, this is the variable you want to modify or you want to protect. So this is comparable with some previous work. This work is for building attacks. And our work is to find some data. This is for building attacks. So time you can say most of the time is comparable. Sometimes we are faster, sometimes they are faster. So which means you can build a pipeline to find the data, to find a bug, and build attacks. You can build everything together to build a chain of exploitation generation. Okay, so here's a case study. This is the V8. V8 is the JavaScript engine. This one is used by Chrome by Microsoft Edge, by Opera, by Node.js. So basically, as long as you use any tool listed here, you're using V8 internal. So this one have 3.5 million lines of code. So if you want to check it manually, go ahead. That take forever. So we do this automatically. We just provide a very simple JavaScript code, and then our tool reviews at least 2 potential variables, and one of them is highly probable. This is a global variable. There are 93 million instructions a test can use to modify this variable to build a tag. And here's the tag. So this is the thing we find. This is the variable we already find. This is the one condition. You can say is if this variable is true, they're going to do this operation. So we just look into it after the tool report is finding. We find this is to control whether the JavaScript code can run arbitrary amounts on your computer. This one is very security related control, which means if you enable this one, if you make this one to true, the website can run any local amount on your computer. So this is a very strong breach of security. So we just use the old tag. This is the old tag. You can see this is 2021 is already been fixed. We reuse this one to build a tag to bypass defense and to modify this one variable to 1. That's it. You don't need to modify this one variable. Attackers can run any command on your computer. So this is a consequence of this problem. So we have a quick demo to show how to build tags. So that. So this is this is the files. This one is a traditional file. We try to run the bash. Bash is the shell. You can get a shell to do anything. So if you directly run this one, you say, no, this is not supported because this one is a very risky function. You have to specify this command line interface, this command option to enable this. But the question is, attackers, they have no way to provide this option because we're going to run this. We're going to run this engine without any permission, without any special commands. So here we just try out exploitation. This is the attack. This is the content of this attack. We just modify one thing, okay? Change something to 1. That's it. So in this case, if we run this attack without providing this option, in case we get a shell, okay? So which means attackers, they don't have the permission even to provide a special option in command line, but they can start a shell on your computer and do whatever they want if they have this bug, if they know this exploitation. Okay, so I think that's pretty much we have. In conclusion, we just provide a tool called Viper that can automatically supporting Syscall-Guard variables for data attacks. We build a solution, branch faults and assessment, and we build a tool and find a bunch of interesting results. We build attacks. This attacks is not a live attack because we use old bugs. This bugs has been fixed, so don't have to worry about it. This is going to have attackers. But the question here is attackers will find new bugs. They can use new bugs and then to attack this data we find and to achieve the similar attacks. So all of this, our code, our attack is available online, so you can find them from this link. If you're interested, you can go and check. We're very happy to discuss with you if you want. And finally, I want to thank our students and co-authors. Most of them are sitting here, Kai and Song and Zhechang. They just joined very recently, last year and this year. And of course, we want to thank our supporters from ASF and ICDS and IST State Funding. Without this, we cannot do our work. And thank you all. And I'm ready for questions. I think we have time for a bunch of questions.
The automated branch test can be per application for use case, but I'm wondering in terms of scalability, how can this be scaled on, say, testing an entire infrastructure, or like how scalable would this approach hypothetically be?
Okay, so about the scalability, this one we'll see something here. So this is the V8. This one has 3 million lines of code. We already support this. Right. Okay, so give you a more concrete the result is Linux kernel. Linux kernel we have 40 million lines of code. Okay, so this is about 1 magnitude larger than this one. So I think in theory you can still support that, but we can imagine a bunch of engineering effort to support this finally.
Right, so that's, let's say, Linux kernel, that's still, I'm thinking more in a sort of theoretical sense, right? Will there be a scenario in the future, if this work would continue, that it can be massively deployed, say into analyzing a full enterprise system, as opposed to individual component of software?
That's a good question. So whether we can support the whole infrastructure of the company of enterprise level, I think we can view this way. For enterprise level, they must have individual tools combined together, right? I cannot imagine anything can be more complicated than browser or kernel. Maybe they have something, but they must be combined by some component, right? For example, V8 here, this one is one component, but this one is a part of the Chromium, of the Chrome browser, is Chrome, right? So in this case, you don't have to test the whole Chrome, you can test the component one by one and find the critical data. I think this is a solution. Even if you have a super complex system, you can always decompose them into different individual components and test one by one, right? Like a browser, like kernel, I think kernel is another good example. You have so many different components in kernel, right? You have the memory manager, you have the process scheduler, you have the device drivers, different components. You can test them one by one. Or even file system is part of kernel, right?
Thank you.
Yep. Yep.
So, thank you for your time. I think it's very easy for you to understand, although I'm not from the security.
Yeah, we know that.
And I wonder if your words.
Hold on a second. Can you use this for the recording?
Oh, sure. Okay, so my question is about what is major for the detection of the offline variable, right? The data. And I wonder how is the next step, right? After it is detected, so what can the company or the developer do to prevent this kind of attack in the future?
Okay, that's a very good question. So what do we do next, right? So of course, we do this one to demonstrate it's possible. Attackers can find these variables automatically, build a test automatically. But our research is, of course, finally comes to defense, right? So our goal here, we can go two directions. The first one is if you find that this is critical to your security of your application, you should protect them, right? So currently, we already have a solution for protection, but the question is that the protection is to make the program very slow. Okay? For example, if you deploy the defense, maybe your browser, maybe Chrome is 10 times slower. You will not use that, right? The reason you choose Chrome is it's faster, right? It beats Edge and IE before. But if you deploy defense, it's slow. But now our solution is that, hey, you don't have to protect all of them. Okay? You can provide the most important, the security critical Syscall-Guard variables, right? If you protect them, then there's going to be less chance for attackers to build attacks. So this is one direction. Find the critical one and protect them using current solution. Okay. And the second one is if we find some variable is super important, and this is maybe single failure location. Okay. Maybe you want to decompose this variable into multiple variables, and to make sure the impact of this corruption is minimal, to reduce its impact. You don't want to use this variable so commonly in the program because we know if you use this one single variable, all security depends on this. Then attacks won't modify this one. They can do a lot of others after modifying this one. So you may want to refactor your code to introduce many duplications and different versions and to customize. You can think about this minimal privilege design, right? You want to make sure only one variable is control one thing. You don't want to use one variable to control too many things. I think this is another direction to explore. Actually, we have the plan to explore this direction. Our research is supported by NSF, and in the proposal, we propose a bunch of directions to build defense. So this is definitely defense is our goal, not attack. But attack is interesting, so I want to show you very quickly with this first result. Thank you.
Thanks.
I really appreciate your work, and your motivating examples were kind of interesting but simplistic, because of course nobody should be using FTP anymore, and we shouldn't be using password stored in our data. But you described that actually, that's the thing that you might address some of the problem. But as I'm looking at this more, I'm thinking, you have suggested a an advancement in the ability to attack the invoice.
Yes, we do that.
And it doesn't matter if we are the defenders or we are the attackers. So your suggestions on things that you might be able to change, you said, okay, well, we don't only want one variable to do one thing. We don't want one variable to do multiple things. But I guess the same thing can be said the other way around. We don't want multiple variables to do the same thing. And if it's the same thing that is the thing that we need to protect, we do want that one variable to do that one thing, right? We don't want 17 variations of ways to go address, whether it's a privileged user or not, and that. So when you make suggestions for modification to developers in the future, you could say, well, don't put all of your eggs in one basket, because if we find the basket, then we can do whatever we want with it. But then if we make multiplied versions of those baskets, we make a mess out of things the other way too. Where's the balance in protecting stuff versus having multiple copies of it that we then have to figure out how to protect those things?
Okay, thank you, Nick. This reminds me in my class, IT 454 forensics, right? You need to find evidence and you need to present your evidence in the court. And during the cross-examination, the lawyer from the opposing side is going to ask you long questions, trying to confuse you, trying to hide some questions. I think you do not do this. So let me repeat the question. So based on my suggestion, you can believe if we have multiple copies of the same variable, maybe they're so complicated, right? Maybe even need to use more attack surface. Should we do this? I think my understanding is it's very interesting. It could be two answers. First one is duplicate a variable. Could be a defense. Okay, so the point is you can duplicate one variable and periodically or randomly check their consistency, right? For attackers, if they modify one copy but they didn't modify another copy, if they check it, you go, oh, this is different. Must be something wrong, right? It's a could be a defense. That's very interesting. Just reminded me. So my original answer to that student is sorry, I see the student. Anyway, so to that question, my answer is we do not want to decompose one. Before you have one variable control so many things, but you want to make sure you may want to split the variable to multiple ones. Each of them control one thing, one minimum thing. Okay, it's like you have one leader control so many things, but you want to separate the position into multiple positions. Each of them will control one particular resources and privilege. So in this case, if attackers modify one of them, they can only get one part of the privilege instead of getting the whole privilege. If they want to, you can modify all variables and get the original privilege controlled by one variable, but it's really more challenging. That's my original proposal. But I think the duplication is one interesting thing. Duplicate and check consistency randomly or periodically, that even make the exploitation much harder. That's really one direction to explore. Does that answer your question? Thank you.
I guess I should go to law school.
I didn't get that.
I guess I should go to law school now.
Oh, yeah, thank you.
Talking about branch exploration. It seems to me that the complexity of that code is exponential.
It could be.
Could be.
We don't know.
Okay.
Yeah, we don't have answers, so whether it's exponential or linear. But usually, if you have more code, definitely they have the connections, right? Have dependencies. That could make it exponential. Could be.
Do you have any heuristic to make it walk linear or linear?
Okay, that's very interesting. That's something I'm not good at that. Theory part. So I think maybe I can answer this way. So many codes is actually encapsulated, right? They are already wrapped up, and then they have APIs, a few APIs, to reach up to external users can use. You don't have to invoke the internal function, just invoke APIs. I think this is one way. This is the one way, like I mentioned, to control the complexity. But the problem is, even these APIs, they're going to invoke other functions internally. Okay, so which means outside users may still have some indirect ways to reach some deeper internal function logic. and then still may corrupt memory and modify anything. I need to remember the memory is actually shared for the whole process. Okay, there's no control, there's no isolation, no protection. The memory is actually shared by all the code inside one process. Okay, even if one memory instruction is corrupted, they may change the whole memory. That's the problem. So currently we do have solutions that trying to provide the in-memory, in-process isolation. Okay, so which means you have a lot of code here. Maybe this code only accesses this part of memory. This code only accesses this part of memory. We have software solution, hardware solution. But the problem is we are making progress, but some questions are not solved yet, right? How do you define the boundary, right? If you draw a boundary, say, hey, your code cannot access this one. What if the original functionality is broken? This is one question. Second one is if you want to cross the boundary, you always need to do something like save the context, switch the context, and do some storage, saving and restoring. This will introduce some overhead. So overhead is our big enemy because the application developers like Google or Microsoft will say, hey, what's the overhead? If you mention more than 5%, they're not interested. They say, oh, this is too much. Users will not buy it, right? If your browser is 5% slower, they believe no one going to use your browser anymore. They're going to lose the market. They're going to lose a lot of brand benefit. So this is a big problem for the control you mentioned or the security we have in memory space. Any other question?
Okay, well, help me thank Dr. Hu.
Thank you for joining. Thanks for all the good questions.
And we're not allowed to have food inside the room, but there's food outside the room waiting for you. You can cook something and you can all gather and talk more outside the room. Please continue.
Thank you. Thanks. Thank you. Maybe I find them to stop them.